Welcome to Talk Tensors. What if I told you that the fundamental math governing probability basically guarantees we will soon never be able to tell the difference between a human being and a machine?
Right, yeah.
And not because the technology isn't good enough, but because the literal laws of the universe just won't allow it.
It is a genuinely jarring thought. I mean, we're so used to this idea that if a digital problem exists, a clever enough engineer can just build a software patch to fix it. We always assume security is just a matter of processing power and ingenuity.
Yeah, exactly. And for a while, the entire tech industry operated on that exact assumption when it came to AI safety. So our mission for this deep dive is to unpack a really landmark AI safety and alignment research paper that completely shatters that comforting illusion for you.
It really does.
We're looking at a mathematical proof showing that reliable AI text detection is fundamentally impossible against a motivated attacker. But to really grasp the weight of this research, we need to take you back to the historical context just before this paper was published. Think about the landscape when those very first, highly capable, massive generative language models dropped.
Oh, the panic was palpable. And I mean, it wasn't just academic pearl clutching, right? The moment models could generate coherent, contextually accurate, and highly persuasive text at an industrial scale, all those theoretical threat models we had debated for years just became terrifyingly real.
Yeah, overnight.
We were suddenly staring down the barrel of automated, highly personalized social engineering for, spear phishing attacks. We're looking at the collapse of trust in digital communication because of infinite low-cost propaganda and fake news.
Not to mention the immediate crisis in education with plagiarism, right?
Yeah.
Students just having essays written for them.
Exactly.
So the safety community's initial response to this existential panic was, frankly, to try and build a massive digital wall. The instinct was to engineer automated detectors.
Yeah, the silver bullet approach.
Right. The prevailing wisdom was that if we could just build a sensor to scan the internet and instantly sort every piece of text into a human bucket or an AI bucket, we could filter out the synthetic slop and neutralize the threat.
And, it makes sense as a knee-jerk defensive posture. If a new, potentially toxic element is introduced into an ecosystem, your first move is to deploy a sensor to track it. And the dangerous thing was, for a brief window, it actually looked like those sensors were working.
Right. The early benchmarks were incredible.
They were. I mean, these detection systems were boasting true positive rates in the high 99th percentile. The whole industry basically let out a collective sigh of relief.
Which brings us to the core thesis of the research we are diving into today.
Yeah.
That relief was built on a complete foundation of sand. The paper proves that as language models get better at their primary job, which is mimicking human data distributions, the ability to detect their output mathematically approaches a coin flip.
It forces a complete paradigm shift. It takes the conversation from, we need a bigger database to catch the AI, to the laws of probability dictate that a perfect detector is a mathematical impossibility.
So here's how we're going to break this down for you today. First, we are not just going to list the security systems the industry built. We're going to trace the logical evolution of how engineers tried to solve this problem, exploring the four main architectures of detection.
Right, the defense side.
Exactly. Then we're going to look at the devastating offensive technique used to break them, which is a method called recursive paraphrasing.
That's where it gets wild.
Oh, it really does. And from there, we'll explore the genuinely dark implications of spoofing, where these broken detectors can actually be weaponized to frame innocent humans. And finally, we will walk through the mathematical theorem, the total variation distance proof, that basically permanently closes the door on the era of AI text detection.
It's a rigorous journey, honestly. It goes from empirical stress testing on live models directly into undeniable theoretical bounds.
Let's start with the defenses. The paper scrutinizes four distinct methodologies, but they didn't all emerge in a vacuum. They evolved as engineers realized the flaws in their previous attempts. The first and most intuitive approach was just brute forcing the problem with what the paper categorizes as trained neural network detectors.
Right. It's the classic machine learning approach. If you want to classify an image as a hot dog or not a hot dog, you just train a neural network on thousands of pictures of hot dogs, right?
Yeah, exactly.
The early AI detectors, like OpenAI's Roberta Large detector, they use the exact same supervised learning philosophy, but for text. You compile a massive data set of known human-written text, and then a massive data set of known AI-generated text.
And you just smash them together.
Pretty much. You feed both into a classification model, and you let the model's hidden layers calculate the really subtle, multidimensional statistical differences between the two.
It's basically treating the AI text like it's a foreign language that has its own specific learnable grammar. But there's a glaring, fatal flaw in that approach, isn't there? The foreign language keeps changing.
That is the absolute Achilles heel of supervised detection. It suffers from severe distribution shift. So, an AI model released in January has a specific statistical fingerprint. But the model released in March, which might be trained on a slightly different data set with a new alignment technique.
It has a totally different fingerprint.
Right. So the neural network detector you trained back in January becomes practically useless by April. You are forced onto this perpetual, agonizing hamster wheel of constantly retraining your detector every single time a new generative model hits the market.
Which is it's unsustainable. So if retraining neural networks is a never-ending nightmare, the natural engineering pivot is to stop looking at the text from the outside and start looking at the math of the generative models themselves, which leads us to the second defense architecture, zero-shot detectors.
Methods like DetectGPT fall into this category, and the elegance of the zero-shot approach is that it requires absolutely zero training overhead.
Wow, okay.
Yeah, no massive data sets, no constant fine-tuning. Instead, it leverages the inherent statistical properties of how a language model actually predicts the next word.
The paper talks about AI text sitting in I think it's called the negative curvature of the model's log probability function. And I really want to unpack that because it sounds like super dense jargon, but the mechanism is actually fascinating.
It's brilliant, really.
Right. So if I'm understanding the math correctly, I like to think of it like bumping a record player. If you take a piece of AI-generated text and you randomly swap out a few words, you perturb it, right? The AI model's assigned probability for that new text violently crashes. The needle scratches right off the track.
That is a highly accurate way to visualize it. Because the AI originally generated the text, that specific sequence of words sits at a local maximum of probability for that model. Like, it is the model's idea of a perfect sentence.
So changing anything ruins it.
Exactly. Any random change you make is mathematically guaranteed to be viewed by the model as a worse, less probable choice.
But if you take human written text and perturb it, the needle doesn't scratch. It just kind of skips to a similar sounding note. Why is that?
Because human text is already suboptimal from the perspective of the AI's probability distribution, the human didn't pick the absolute highest probability tokens according to the AI's weights, Yeah. The human picked words based on human idiosyncrasies, emotions, style.
Right.
So if you randomly swap words in a human sentence, the AI model's probability score for that sentence might go down a little, or it might even go up. It doesn't experience that sharp, violent crash, that negative curvature that perturbed AI text experiences.
So the detector just takes a suspicious text, changes a few words, and checks to see if the probability score plummets. But wait, to check the probability score, you need to be able to look under the hood of the model.
You've hit on the exact limitation.
Yeah.
To map that curvature, a zero-shot detector requires white box access, or at least highly permissive API access, to the original source model that actually generated the text. So if an attacker uses a closed source model that doesn't expose its log probabilities, or if you simply don't know which of the hundreds of open source models on the market generated the text, your zero-shot detector is flying totally blind.
Okay, so Pillar 1 requires endless training data. Pillar 2 requires access to the source model's internal math. Because both of those are just wildly impractical for scanning the open internet, the security community pivoted to Pillar 3. And this is the one that got all the mainstream media hype, watermarking.
And from a purely cryptographic standpoint, watermarking is brilliant. Instead of acting like a detective trying to spot accidental clues after the crime has happened, watermarking forces the AI to leave a deliberate, invisible signature in everything it writes.
Right. The paper specifically examines the robustness of a widely discussed soft watermarking scheme. But walk us through the mechanics of that invisible signature. Like, how do you force a machine to watermark a paragraph without making it sound like a malfunctioning robot?
It relies on manipulating the model's vocabulary at the exact moment of generation using a private pseudo-random number generator, or PRNG. Yeah. Every time the model is about to predict the next word, the next token, the PRNG looks at the previous token and uses it as a cryptographic seed. Based on that seed, it silently partitions the model's entire dictionary into two lists: a green list and a red list.
So if the previous word was the PRNG mathematically shuffles the dictionary and says, okay, apple, car, and dog are now on the green list, but banana, truck, and cat are on the red list.
Precisely. And then the model is mathematically biased. Its logits are artificially boosted so that it is overwhelmingly likely to select its next word from the green list.
But because the dictionary is so massive, there are always plenty of perfectly logical, grammatically correct words on the green list for it to choose from.
Right. It doesn't break the grammar.
So the semantic meaning is completely preserved. To a human reading the essay, it looks totally normal.
But to the detection algorithm, which holds the private key to that pseudo-random number generator, the text is practically screaming its identity.
Wow.
The detector simply reads the text, recreates the green list using the private key, and counts the tokens. If a piece of text has a statistically impossible density of green list words, say 90%, when random chance would dictate 50%, the detector flags it with absolute mathematical certainty.
It's an incredibly elegant solution. But it relies entirely on the honor system, doesn't it? It requires the developer of the AI model to actually implement the watermark and take the performance hit.
Sadly, yes.
Which leads us to the fourth, most draconian and final pillar, retrieval-based detectors.
Right. If you can't rely on subtle cryptography, you resort to a brute force ledger. A retrieval-based detector acts as an omniscient database. It basically permanently logs every single output ever generated by the LLM into a massive vector database.
When you say vector database, we're talking about embedding the text, right? Turning sentences into coordinates in a high-dimensional space so you can measure how close they are to each other, mathematically speaking, like a vastly more sophisticated version of the plagiarism software Turnitin.
Yes, exactly. It uses cosine similarity to measure semantic closeness. When a user queries the detector with a suspicious document, the system embeds the document and searches the giant database. If it finds a semantic vector that is suspiciously close to a logged AI output, it flags it.
Okay, let's unpack this. It sounds like we built 4 different kinds of security cameras. One looks for known uniforms, which is the neural approach. One looks for robotic walking patterns, the zero shot. One puts invisible ink on the shoes of the robots, the watermark. And one just keeps a ledger of everyone who left the factory, which is retrieval.
That's a perfect way to summarize it.
Right. So if these detectors had a 99.8% true positive rate, why was the safety community still worried?
What's fascinating here is the difference between a benign environment and an adversarial one. The baseline metrics assumed the AI text was left completely untouched. They assumed an environment where someone prompts an AI, copies the output, and pastes it directly onto a blog without changing a single comma.
It's a completely passive user.
Exactly. But real-world bad actors, the state-sponsored propagandists, the automated phishing rings, they don't leave their text untouched. They are actively motivated to evade your sensors. You have to stress test the system against an adversary who is actively trying to break it.
And that transition from theory to a live adversarial stress test is really where the illusion of safety crumbles. This brings us to the core attack vector developed in the paper, the recursive paraphrasing attack. We know how the defenses work. Now let's watch an attacker dismantle them.
The premise of the attack is just elegant in its simplicity. Let's say you're an attacker who wants to generate a highly sophisticated, persuasive piece of disinformation. To get the best reasoning and the most fluent writing, you really want to use a massive, state-of-the-art language model. Let's say a 13 billion parameter model, like OPT-13b.
But OPT-13b has the soft watermark enabled. It's blasting that cryptographic signature. If you just publish the output, the detector catches you with 99.8% accuracy. So a listener might ask, why not just use a smaller, unwatermarked model to write the fake news in the first place?
It comes down to what we call capability overhang. The smaller open source models might not possess the deep reasoning or persuasive nuance required for a highly targeted psychological operation.
They just aren't smart enough yet.
Right. The attacker needs the intellectual horsepower of the massive detectable model. They need the payload. They just need to scrub the signature off of it.
It is literal money laundering, but applied to the statistical fingerprints of a neural network.
That's the perfect way to look at it. The attacker uses a 2-step pipeline. Step 1, generate the high-quality payload with the detectable model. Step 2, feed that payload through a second, completely different model, a paraphrasing model, to launder the text and wipe the original cryptographic signature.
And the researchers didn't just theorize this, right? They built it. They tested 3 different neural network architectures as their laundromats.
It did.
They used DIPDR, which is a massive 11 billion parameter model explicitly trained for paraphrasing. They used Meta's Llama 27B chat, steering it with system prompts to act as a paraphraser. And to prove that you don't even need massive compute to pull this off, they used a tiny, lightweight 222 million parameter model based on the T5 architecture.
But the true devastation of this attack vector lies in the word recursive.
Right.
The attacker doesn't just push the text through the paraphraser once. A single pass might leave residual traces of the original green list distribution.
So they loop it.
They loop it. They take the output of the first paraphrasing pass, and they feed it directly back into the paraphraser as the new input. The paper tracks these iterations meticulously, denoting them as PP1 for the first pass, all the way up to PP5 for 5 rounds of recursive paraphrasing.
Okay, let's look at the absolute carnage this causes to the detection metrics, because it is staggering. Let's start with our strongest defense, the watermark, which was sitting at a 99.8% true positive rate. What happens when the attacker hits it with this recursive laundering?
The drop is immediate and catastrophic. After just one single round of paraphrasing PP1 using the Llama 2 model, the detection rate plummets from 99.8% down to 54.6%.
Just one pass through a standard open source chat model, and almost half of the watermarks are destroyed. That's insane.
And it continues to degrade. By the time you reach 5 rounds of recursive paraphrasing, the detection rate drops below 20%.
Wow.
But the researchers went a step further to simulate a truly optimized adversary. They modeled a scenario called the best of Appy attack.
This assumes the attacker has black box access to the detector, right? Like they can't see the code, but they can submit text and see if it gets flagged.
Correct. So in this scenario, the attacker takes their original payload and generates 5 distinct recursively paraphrased versions -PP1 through PP5. They query the detector with all 5 versions. They look at the scores, and they simply publish the version that achieved the lowest detection confidence.
And what's the result?
Under that highly realistic scenario, the watermarking detection rate drops from 99.8% to a catastrophic 4.0%.
4%. Let that sink in for a moment. 96 out of 100 pieces of watermarked machine-generated propaganda are slipping through the net completely undetected. The invisible ink was completely chemically washed out by the recursive loop.
And the other defensive pillars fared no better. Let's look at the zero-shot detectors, the ones relying on the negative curvature of log probability. The researchers measured this using the AUROC metric.
Right, and just to ground this for you listening, AUROC stands for Area Under the Receiver Operating Characteristic Curve. It's a fundamental metric in statistics. An AUROC of 100% means your detector is literally perfect. An AUROC of 50% means your multi-million-dollar neural network is performing exactly the same as if you just flipped a coin.
Right. And before the attack, the Detect-GPT zero-shot method had a highly respectable AUROC of 96.5%. After recursive paraphrasing, that metric plummets to 25.2%.
Wait, 25.2%? That is actively worse than a coin flip.
Yes.
The paraphrasing warped the text probability curve so severely that the detector is consistently, aggressively wrong. It is actively confusing the system.
It absolutely inverts the signal. The trained neural network detectors, like OpenAI's Roberta, dropped from 100% true positive rates down to roughly 60%. Even the final pillar, the giant brute force retrieval database tracking semantic similarity, dropped from perfect accuracy to below 60% after 5 rounds of laundering.
So even the database got beat.
Yep. The semantic vector had drifted just far enough from the original log to avoid triggering the cosine similarity threshold.
Now, I have to play devil's advocate here. Because my immediate thought when I read recursive paraphrasing is that if I take a pristine, meticulously researched news article and I run it through an automated synonym swapping bot 5 times in a row, well, the result is going to be unreadable, garbled nonsense. It's like the old game of telephone.
That's a very fair assumption.
Right. So if the cost of washing off the AI signature is that your propaganda becomes a confusing mess of broken English, then the defense technically still wins, doesn't it? Because the attacker's payload is effectively ruined.
That is a critical pushback, and the researchers anticipated it entirely. An attack is only viable if the utility of the text is preserved. This is what the paper refers to as the quality trade-off. To rigorously measure this, they couldn't just test the attack on simple, 140-character tweets.
They needed real data.
Exactly. They evaluated the degradation across highly complex data sets to measure distribution shifts in different domains. They used Exum, which consists of long-form news articles, PubMed QA, which is dense, highly technical medical text, and the Kafka dataset, representing SEO and marketing copy.
So they stress the laundering process on text where precision, factual accuracy, and logical flow are paramount. How do you even mathematically measure if a text is still good after all that?
They deployed a two-pronged evaluation strategy: large-scale human evaluation and rigid automated benchmarks. For the human element, they crowdsourced workers via Amazon Mechanical Turk. They presented the human evaluators with the original unparaphrased AI payload alongside the text that had survived 5 rounds of recursive laundering.
And it didn't tell them which was which.
Right. A blind test. They asked the humans to rate both content preservation and grammatical fluency on a 5-point Likert scale.
And what did the human eye see? Was it garbled?
Not even close. When using the 11 billion parameter DI-Peeper model as the paraphraser, a full 70% of the heavily recursively laundered passages maintained high-quality content preservation.
Wow.
The core narrative, the facts, the persuasive thrust were entirely intact. Furthermore, 89% of the laundered passages maintained high-quality grammatical fluency. To a human reader, the text was indistinguishable from natural prose.
But I mean, human evaluators can be easily tricked by smooth grammar, right?
Yeah.
They might miss a subtle degradation in the underlying logic of a medical text. That's why you need the automated metrics.
Precisely. To test the logical rigidity of the text, they utilized the SQUAD v2 benchmark. SQUAD stands for Stanford Question Answering Dataset. It is a brilliant way to test semantic meaning. You take a complex context passage and you ask an AI model to answer reading comprehension questions based solely on that passage.
So it's essentially a standardized reading test for algorithms.
Yes. On the original pristine AI text, the model was able to accurately answer the comprehension questions 97% of the time.
Okay, that's our baseline utility, 97%.
Then, the researchers recursively paraphrased those exact context passages 5 times, completely washing away the detection signatures. They then asked the model to answer the exact same comprehension questions using only the newly laundered text.
And the score?
The accuracy only dropped to 95.5%.
A 1.5% drop in structural comprehension. That is the smoking gun of this entire section. The semantic meaning, the factual relationships, the logical arguments, they all survive the laundering process almost perfectly. The utility survives, but the cryptographic fingerprint is obliterated.
If we connect this to the bigger picture, it tilts the entire risk-reward calculus in favor of the adversary. If you were a hacker launching 1 million highly targeted phishing emails or a state actor flooding social media, you will happily accept a microscopic 1.5% drop in text perplexity if it guarantees your payload evades the platform's security filters 96% of the time. The defense illusion is broken.
But the paper doesn't start at evasion. Evading a detector is what we call a type 2 error in statistics, a false negative. The detector says human when it's actually AI. That's a massive problem for platform integrity. But we are about to transition into a realm of this research that is significantly darker and, frankly, much more dangerous for everyday people.
This is the scary part.
Because the paper proved that adversaries don't just use these vulnerabilities to hide themselves. They can actively invert the mechanisms to frame innocent humans. We are moving from the realm of hiding into the realm of spoofing, forcing a type I error.
Yes, a false positive. The system falsely detecting a completely original human-written text as an AI construct. And the paper demonstrates how the specific architecture of these detectors can be weaponized against us.
Let's start with spoofing the watermark, because on the surface, this sounds impossible. We established earlier that the pseudo-random number generator that creates the green list of words is cryptographically private.
Right. The key is hidden.
The key is locked on the developer server. If an attacker doesn't have the source code, if they don't have white box access, how can they possibly spoof a watermark they can't see?
They achieve it through brute force statistical inference. The key might be hidden, but the AI's output is public. If you observe the output long enough, the cryptography begins to leak. The researchers simulated an attacker who simply queries the target watermarked model, in this case, OPT 1.3b, repeatedly. They generated 1 million tokens of text.
1 million queries, just sitting there watching what words the model tends to pair together.
Exactly. They are conducting an exhaustive analysis of token pair distributions. If they observe that the word the is followed by the word apple highly disproportionately compared to normal human text, they can statistically infer that when the is the prefix, apple is currently sitting on the hidden green list.
It's like watching a rigged roulette wheel for a week straight until you figure out which numbers have magnets under them.
That is exactly what it is. And the most shocking part is that the attacker doesn't even need to reverse engineer the entire dictionary. The researchers found that they only needed to estimate a proxy green list for the 181 most common words in the English language.
Just 181 words that mapped a tiny fraction of the invisible ink.
But it is enough. Once the adversary possesses that 181-word proxy list, they can launch a manual spoofing attack. The attacker sits down at their keyboard and writes a passage of text entirely from scratch. It is 100% human-generated.
Okay.
But as they write, they deliberately construct their sentences to heavily favor those 181 specific words they know are flagged as green by the system.
And when they feed that human-written, artificially constrained text into the official watermark detector,
the detector reads the text, sees a statistically impossible density of green list tokens, and its confidence metric spikes. In the researchers' empirical test, this manual spoofing attack dropped the detector's AROC from a pristine 99.8% all the way down to 1.3%.
Oh, God.
The mathematical system is absolutely fundamentally convinced that the human text is a watermarked AI output.
Here's where it gets really interesting. Think about the real-world implications of that vulnerability. Let's say a bad actor writes a deeply offensive, highly illegal, or politically compromising manifesto. They manually inject the 181 proxy green list words, and they publish it anonymously online.
Yep.
When journalists, researchers, or law enforcement run that manifesto through the official detector, the software will mathematically certify the text was generated by a specific company's AI model. An attacker can artificially engineer a massive PR or legal crisis for an AI developer.
Or, more chillingly, they can use it to destroy the reputation of a human rival. If you know a platform uses a specific detector, you can spoof the signature to ensure your competitor's human work is flagged and removed as automated spam.
It's just devastating.
And the spoofing vulnerabilities aren't limited to the elegant cryptographic watermarks. The brute force retrieval systems, the giant databases logging everything, are susceptible to a vector that is terrifying in its everyday, mundane applicability.
The paper calls this the database poison pill. I want you to walk us through this scenario because this is the exact kind of thing that is probably happening in high schools and universities right now.
Imagine a university setting. A student spends weeks researching and writing a brilliant, entirely original essay. It is a 100% human effort. They submit the physical or digital document to their professor.
Okay, totally normal so far.
Now imagine that professor, perhaps maliciously trying to build a case against the student, or perhaps just carelessly out of curiosity, takes the student's original essay, pastes it into a model like ChatGPT, and prompts it. Rewrite this essay for clarity.
Okay, so the AI spits out a slightly altered, paraphrased version of the student's original work.
Yes. But recall how the retrieval-based detector functions. By its very design, it permanently stores every single output the AI generates into its secure ledger to use as a baseline for future detection. The moment the AI outputs that paraphrase, it logs it into the AI-generated database.
Oh, this is a disaster.
It is a systemic trap. A week later, the university's automated plagiarism software runs the student's original submitted essay against the central database. The retrieval detector performs a cosine similarity search, embeds the student's essay, and finds an almost identical semantic match sitting right there in the official AI-generated ledger.
So it flags it.
It immediately flags the student's original work as a 100% semantic match for machine generation.
Because the professor fed the text to the AI essentially stole the student's cryptographic timestamp. The system now views the AI as the original author, and the human student as the copycat. The teacher has, inadvertently or purposefully, framed the student for academic fraud. And the worst part is there's an unassailable official digital log confirming the accusation. If the student claims they wrote it, the administration just points to the database and says, the math says otherwise.
It is a devastating irony. The exact architectures deployed to preserve academic integrity and objective truth can be trivially inverted to ruin human reputations. It highlights a fundamental, inescapable tension in alignment theory, the rigid mathematical trade-off between type I and type 2 errors.
Explain that tension. Like, why can't we just tune the detector to avoid framing the student?
Because probability is a zero-sum game in this context. If you tune your detector to be incredibly sensitive and aggressive at catching AI text, meaning you want to lower your type 2 evasion errors, you invariably, mathematically, must increase the rate at which the system hallucinates and falsely accuses humans, which are your type I errors.
So the seesaw.
Right. If you broaden the net to catch the recursive paraphrasing, you catch innocent humans in the crossfire. Blindly trusting these post hoc detection systems carries immense tangible reputational risk.
Which brings us to the existential question of this entire deep dive. We've seen the empirical hacks. We've watched recursive paraphrasing chemically wash away the cryptographic signatures. We've seen how spoofing algorithms can frame a high school student.
Yeah.
But a techno-optimist listening to this might say, look, this is just a snapshot of early software. Early systems are always flawed. We don't abandon cybersecurity just because the first firewall got breached. We just need to engineer a better detector. We need a massive neural network, a more complex zero-shot metric, a watermark that uses a dynamic rotating green list. Does this paper leave room for the hope that a perfect, uncrackable AI detector is just a few engineering cycles away?
It emphatically does not. And this is the pivot that elevates this research from a very clever cybersecurity demonstration into a foundational paper in AI alignment. In Section 4, the researchers answer the techno-optimist with a rigorous mathematical no.
A hard no.
They provide a theoretical proof that rigidly bounds the absolute maximum capability of any detection algorithm, whether it exists today or is invented 100 years from now.
This is where we hit the bedrock. We're moving from empirical observation to theoretical limits. Let's break down this proof. The paper presents what they call Theorem 1. I want you to translate the engine of this proof into plain English for us. What is the core mathematical concept driving this death knell for detectors?
The engine of Theorem 1 relies on a concept from probability theory called total variation distance, or TV distance.
Okay.
Simply put, TV distance is a mathematical measure of how fundamentally different two probability distributions are from one another. It measures the maximum possible difference between the probabilities that two distinct distributions assign to the exact same event.
Okay, let's ground that. In our context, what are the two distributions we are comparing?
We are looking at the vast high-dimensional space of all possible text sequences. Distribution H represents the true distribution of human-generated text, all the quirks, the vocabulary choices, the sentence structures that humans naturally produce.
Got it. And the other?
Distribution M represents the machine-generated text, the probabilities assigned to text by the AI model.
So if the TV distance between distribution H and distribution M is exactly 1, it means the distributions have absolutely zero overlap. They are mathematically distinct entities.
Right.
It would be like comparing a Shakespearean sonnet to the binary code of a JPEG file. Any detector could instantly tell them apart.
Precisely. Conversely, if the TV distance is exactly 0, the distributions are perfectly mathematically identical. The machine is generating text with the exact same probability weights as the aggregate human population.
And Theorem 1 proves that the effectiveness of a detector is locked to this distance.
The theorem mathematically proves that the absolute best possible AUROC, the maximum theoretical accuracy ceiling of any conceivable detector, is strictly and permanently bounded by the TV distance between the human text and the AI text.
Walk us through the actual equation.
The equation states that the AUROC is less than or equal to 1/2 plus the quantity of TV distance minus TV distance squared, divided by 2. So 12 plus the TV variable math.
Okay, let's play with those variables. As language models get more advanced, their explicit design goal is to perfectly model human language, which means, over time, distribution M is constantly moving closer to distribution H. The TV distance is shrinking.
And as that TV distance variable shrinks and approaches 0, look at what happens to the right side of the equation. The entire fraction part collapses towards 0. You are left with AUROC is less than or equal to 1/2, 0.5.
And as we established when we were looking at the zero-shot benchmarks, an AUROC of 0.5 is the exact mathematical equivalent of flipping a random coin.
Yes. The theorem proves that if the generative model perfectly mimics the human distribution, no detection algorithm in the universe, regardless of how complex its neural network is or how much compute power you throw at it, can perform better than random chance. The limitation isn't a lack of engineering creativity. The limitation is the fundamental laws of probability.
But wait, I have to push back here. A skeptic could look at that equation and say, that's a beautiful theoretical bound on a chalkboard. But in the real world, maybe TV distance will never actually approach 0. Maybe AI will always have a slight, detectable algorithmic accent. Maybe language is too complex for a machine to perfectly map.
It's a fair question to ask.
Right. Did the researchers just theorize this mathematical collapse? Or did they actually prove that TV distance is actively shrinking today?
They proved it empirically. They didn't just leave it on the chalkboard. Now, measuring the exact objective TV distance of something as unimaginably vast and complex as the entire English language is computationally intractable. So, to prove the bound, they designed an experiment using synthetic text data where the underlying distributions could be perfectly flawlessly calculated.
How do you build a synthetic language to test this?
They trained single-layer LSTM networks, long short-term memory models, which are an older, simpler architecture of neural nets of varying sizes. They started with tiny models containing only 16 hidden dimensions and scaled them up to 128 hidden dimensions, training them to mimic a predefined synthetic language distribution. By controlling the environment, they could definitively track the TV distance.
And what did the synthetic data reveal?
It revealed a consistent, undeniable trend. As you increase the size, the hidden dimensions, and the capability of the model, the TV distance between the model's output and the target distribution objectively, measurably shrinks. They then mapped this exact same trend onto real-world language using the GPT-2 family of models, tracking the distance from the tiny GPT-2 small all the way up to the massive GPT-2 XL.
So the scaling laws apply to the evasion. As the parameter count goes up, as the model gets smarter, more complex, or more articulate, the TV distance inherently closes.
That is the ultimate paradox of AI alignment revealed by this paper. The very act of making an AI model more capable, more fluent, and better at generating useful text is the exact same mathematical mechanism that destroys our ability to detect it. The primary goal of LLM training to perfectly map and reproduce the human data distribution is diametrically fundamentally opposed to the goal of post-hoc detection. As generative capabilities approach perfection, detection capabilities must approach zero.
So what does this all mean? If the mathematical ceiling is collapsing as models get smarter, and we have the empirical proof that recursive paraphrasing can shatter the defenses that exist today, does this mean the entire research agenda of AI text detection is a dead end? Should we just give up?
This raises an important question about the allocation of resources in alignment research. The takeaway isn't that security is pointless. The takeaway is that post-hoc detection, the strategy of trying to catch the malicious text after the model has already generated it and released it into the wild, is a losing battle against the laws of math.
Because the math always wins.
Exactly. If we cannot rely on catching the output, the safety community must heavily shift its focus and its funding toward pre-deployment alignment.
We have to fix the models on the inside, not try to build X-ray cameras on the outside.
Exactly. The focus must be on constitutional AI, reinforcement learning from human feedback, and intrinsic alignment. We have to ensure that the core weights of the model refuse to generate the harmful content, the fake news, or the malicious code to begin with. We have to secure the generative process at the source, at the moment of inference, because once that text is out of the model, Theorem 1 guarantees it is mathematically destined to blend seamlessly into the human background noise.
It is a complete paradigm shift for cybersecurity. Okay, before we wrap up, it's time for our novel notions segment. Just a quick but firm disclaimer to you listening. This segment is purely speculative. We take the rigorous, proven mechanisms from the paper we just discussed, and we extrapolate them into outlandish but technically plausible future research ideas. It's a sci-fi thought experiment grounded in the math we just learned, mostly for entertainment.
I love this part.
So I have a pitch for you. I call this research agenda benevolent spoofing for privacy.
I am highly intrigued. What is the scenario?
So the paper proved two distinct vulnerabilities that I want to forcefully combine. First, an adversary can use statistical inference to uncover hidden watermarks. They found that 181-word proxy green list just by querying the model a million times. Second, they proved that recursive paraphrasing can fundamentally alter the cryptographic signature of a text without destroying its meaning.
Right, the laundering process.
Now let's flip the alignment script. Usually we think of evasion and spoofing as tools for hackers. What if we use these exact techniques defensively? Imagine a near-future authoritarian regime. This state utilizes massive state-backed language models to continuously monitor and censor the internet.
A very real possibility.
And let's say this regime forces all state-approved internet service providers to route traffic through AI text detectors. They use these detectors to specifically filter out, flag, and track human-generated dissident text, while prioritizing and whitelisting what they deem to be benign, state-approved AI-generated media.
It's a dystopian inversion of the problem. The detector isn't deployed to stop AI spam, it's deployed to hunt human thought.
Exactly. So what if privacy advocates and open source developers build communication tools that use recursive paraphrasing and spoofing to protect human dissidents from this mass automated surveillance?
Oh, I see where you're going.
If an activist needs to send a highly sensitive human-written political email, their privacy client intercepts the message. It automatically recursively paraphrases the text, but crucially, it instructs the paraphraser via a system prompt to heavily inject the 181 proxy green list tokens that the activists have inferred from the state's own watermark surveillance AI.
Ah, you are wrapping the human dissident's original text in the cryptographic camouflage of the state's own approved algorithm.
Right. The first experiment to prove out this research agenda would be incredibly straightforward. We take a known data set of highly sensitive human-written political journalism. We run it through a DI peeper paraphraser that has been explicitly instructed to favor our predefined 181-word proxy green list. Then we run that altered output through a simulated state surveillance filter. We test whether the filter misclassifies the highly sensitive human text as benign, hallucinated AI slop. By deliberately triggering a type I false positive error on the surveillance state's detector, we effectively render the human invisible to the algorithm. We use spoofing to hide in plain sight.
It is a brilliant and honestly entirely plausible application of the paper's findings. You are leveraging the inescapable mathematical trade-off between type I and type 2 errors as a dynamic privacy shield. If the state detector is aggressively tuned to catch all human text, its false positive rate must mathematically skyrocket when faced with adversarial spoofing, rendering their dragnet entirely useless. It perfectly illustrates how an offensive technique in one context becomes a critical privacy defense in another.
Exactly.
And that leads me to a final provocative thought for you to mull over as we end this deep dive. If Theorem 1 truly holds, if the TV distance collapses and AI and human text become mathematically and completely indistinguishable, then the entire concept of verifying content based on its linguistic structure is dead.
It's just over.
It's over. In the future, the value, the authenticity, and the trustworthiness of communication won't be determined by how the text was generated or what linguistic quirks or negative curvature it possesses. It will rely entirely on the cryptographic verification of who sent it. We are likely witnessing the final days of the era of content detection and the necessary, urgent birth of an era of strict cryptographic identity verification. If you cannot prove exactly who you are with a secure digital key, the text you produce, whether human or machine, will hold zero weight in the digital public square.
A completely trustless text ecosystem. That is a heavy but vital thought to leave on. Thank you so much for joining us on this deep dive. As always, the link to the full research paper is in the description below. Stay curious, and we'll see you next time.